Hello everyone, this is Wenbo Yu, a research assistant professor at the University of Maryland, Baltimore School of Pharmacy, and at the Computer-Aided Drug Design Center led by Dr. Alexander McRae. I was invited to give a talk at the workshop, but due to my personal issue, I couldn't make it to Leiden, so decided to deliver my talk virtually. Today, I'm going to talk about the recent progress on developing the SILCS method, basically talking about how we can apply our SILCS method to study ligand dissociation kinetics. Free energy evaluation of binding process of ligand to its target is a routine job nowadays. And the mainstream methods such as free energy perturbation (FEP) solves the problem by estimating the free energy difference in alchemical transformation of a ligand. So in practice, the transformation between the two thermodynamic states is replaced by a series of transformations between intermediate states along a pathway that connects A to B. However, such FEP method relies on ensemble average from a single state, only converge properly when the difference between the two states is small enough. Alternatively, we have the method such as BAR, which utilize configuration information from both two states to estimate free energy differences more rigorously. Nonetheless, all these methods require an ensemble of confirmations, and convergence is challenging considering their expensive computational cost. At the CAD center here, we approach the free energy estimation problem through pre-computing an ensemble of functional group distributions instead of generating ensembles for each ligand. Such pre-computed ensembles can then be used repeatedly in a fast fashion to evaluate binding of ligands. This approach is named as the site identification by ligand competitive saturation, or SILCS in short. And together with the charm general force field, which can describe drug-like molecules using molecular mechanics, enables fast binding estimation for thousands of ligands on a daily basis. SILCS is a functional group mapping approach which offers rigorous free energy evaluation of functional group binding for the entire 3D space in and around a macromolecule. That includes macromolecule flexibility and explicit solvent-solute representation. After the SILCS simulations, by being atom occupancies of different functional groups from the MD simulation, these functional group binding patterns, or so-called frag maps, can provide qualitative information about the preference of bindings of these functional groups. And furthermore, normalize these occupancy maps by the bulk phase occupancies in a Boltzmann transformation formula yields a free energy like term. We call it grid free energy, or GFE, and this enables the quantitative use of the frag maps. Shown here is an example of frag maps generated for the protein PTP1B, and different colors indicate different chemical types. And by visualizing frag maps at a favorable grid free energy ISO value, can provide us about the binding preferences of different functional groups targeting this protein. In addition to frag maps, an exclusion map is also generated based on the regions of the system that are not sampled at all by any of those probe molecules we used in our SILCS simulation, including water. So therefore, the exclusion map represents a strictly inaccessible surface, and the use of such exclusion map instead of a rigid protein surface in a docking study has a benefit to take protein flexibility into account and enable the sampling of inaccessible regions for ligand binding if you just use one rigid protein structure. SILCS method was verified previously to be able to reproduce experimental ligand binding free energies to a satisfactory level of accuracy, and compared to the FEP method on the tested protein systems, the computational efficiency is far more better. Even though the binding affinity is an important term for ligand design, More and more studies have shown that the drug efficacy correlates better with drug binding kinetics than binding affinity alone. High binding affinity doesn't necessarily indicate longer residence time of a ligand stay in the binding pocket. In order to study ligand dissociation kinetics computationally, MD simulations with enhanced sampling techniques can be used, but it's very time consuming and thus is not suitable for large-scale binding kinetics evaluation, especially when you're considering early-stage drug discovery. So here we explore the possibility of using SILCS pre-computed maps to study ligand dissociation kinetics. Here we put together a workflow based on the SILCS method, including ligand dissociation pathway detections, unbinding friendly evaluations, and further machine learning models in order to predict key-off values. And the workflow is fully automatic. I will go through every aspect in this workflow in the following slide. The workflow starts with pathway identification. There are many geometric and topologic analysis-based pathway detection techniques in existence. They usually first convert the protein space into 3D grid or Voronoi diagram representation, and then apply a shortest pathway finding algorithm such as Dijkstra's search algorithm in order to determine pathways between a starting point, which usually is the binding site coordinates, and protein boundary points that defines the boundary entering the bulk phase. As SILCS generate frag maps in a grid format, 3D grid representation of a protein occupying space is naturally selected in our approach. Thus, the issue to be solved here is how we can navigate our path-finding algorithm to find efficient dissociation pathways for ligand using these frag maps. Pathway identification need an effective pathway finding algorithm, and well-established algorithms such as the Dijkstra's search algorithm as used in some other pathway finding algorithms can be employed. And compared to the Dijkstra's search algorithm, there is also an informed variation named A-star algorithm, which uses the best first search and thus can speed up the whole path finding process. And here we decide to use the A-star algorithm as our pathway finding method. To use the A-star algorithm, two functions need to be defined, a cost function and a heuristic function. The cost function defines the cost going to the next grid point, and the heuristic function, which usually adopts the Euclidean distance formula, estimates how far away from the destination and can guide the search approaching the destination faster. Under SILCS, we use both exclusion map and GFE maps in our cost function. The exclusion map defines the void space a ligand can travel, while GFE maps can bears the path toward binding favorable regions. And the weighting factor is also added in order to balance the two functions to let the search access more binding favorable regions while reach the destination as soon as possible. A star algorithm requires two defined coordinates for starting and ending points. In our case, the starting points refer to the ligand binding site, and ending points should reside in the bulk phase surround the protein. To sample all possible dissociation pathways, ending points in different directions should be reached. We approach this goal by mapping Fibonacci lattice onto the surface of a sphere covering the protein. And in this way, all these mapped Fibonacci points represent for the bulk phase boundary for this protein. Since the Fibonacci lattice points are on the sphere covering the maximum dimension of the target protein, these points are apart from the protein surface unevenly. Some points may be far away from the real protein surface, while others are nearby. Some pathways ending at the neighboring lattice points may share the same routes in the protein interior and only dividing in the bulk solvent. Thus, raw pathways need to be trimmed in order to make fair comparison. So first, the nearest protein atom for each Fibonacci lattice point is determined with the distance calculated. And then we can draw all these spheres and to define the spherical spaces around each lattice points. For each raw pathway, any coordinates within the sphere defined by all lattice points centered spheres are removed from the pathway, and only outsiders are retained. Through this straightforward protocol, pathways are truncated promotely after entering the bulk phase. Once all possible pathways are generated, they can be further clustered into pathway clusters. When comparing two rows with different lengths, simple geometric distance used as clustering metric can be problematic. Here we borrow the dynamic time warping DTW method, and it offers an optimal pairing solution between elements from two sequences that do not perfectly sync up with each other. And we use such DTW method to help us to do the pathway clustering. We tested our pathway finding protocol on a haloalkene dehalogenase. As reported previously, as shown on the right, a total of 5 pathways that can help to release the dehalogenation products for this protein was identified. This include the pathway P1, P2A, P2B, P2C, as well as P3. And as shown on the left, our protocol finds 4 out of 5 pathways, which suggests that for this protein, a drug-like molecule prefers the 4 pathways but not P2C pathway. Actually, it was reported previously that the pathway P2C was only found in 1 mutant for this protein in order to release the dichloropropene molecule. And for the wild type of this protein, P2C was only found for exchange of motor molecules and occurred rarely in the extensive MD simulations. So our protocol found ligand and binding pathways that are consistent with these findings, since our protocol is designed to determine the dissociation pathways for big ligand. We also generated pathways when only considering the geometry criteria. So for example, we are only using our exclusion map in our cost function, and in this case, we only generate pathways that satisfying the geometric criteria. And in this way, all pathways can be identified. This indicates that our method using frag maps offers more insights into real ligand dissociation circumstances. In order to further compute a ligand binding free energy profile along the pathway, we convert pathway clusters into slab spaces along the main direction of a pathway cluster in order to sample ligand binding poses efficiently. Based on the cluster center pathway, cylinder spaces at each pathway point are determined based on all pathways in that cluster. And these cylinder spaces are being sampled using SILCS Monte Carlo docking in order to generate binding profiles along the unbinding pathways. Unbinding kinetics of benzimidine from trypsin is a well-studied system by many other enhanced sampling MD methods previously. And from this paper, the authors accumulated about 50 millisecond trajectory data using the accelerating biomolecular dynamics ACE-MD method. And from there, they constructed a Markov state model where they determined 3 metastable states other than the crystal binding state. And using our SILCS kinetics workflow as shown on the left, we determined 3 most populated pathway clusters, and these 3 clusters lead to 3 metastable states on the protein surface as shown. And these 3 states actually reproduce the 3 metastable states constructed from the MSM model. The LGFE values evaluated from these 3 states are in the consistent order as reproduced reported relative free energies with state S3 has the lowest value. We can also quickly examine the energy profile along the pathways in SILCS kinetics and estimate energy barriers that might be linked to the ligand residence time. The energy barriers estimated for relocating benzimidine from the active site to other metastable states are evaluated. And as shown here, you can see the S3 state has the lowest barrier among all, which is very consistent with the reported PMF surface in the previous work. So you can see, as reported, their constructed PMF showing that the energy barrier between the active site state and the metastable state S3 has the lowest energy barrier among all other metastable states. Since SILCS kinetics can quickly generate binding pulses along the pathway, one can examine these binding pulses closely along the pathway to interpret interactions and contributing factors to the unbinding events. For the pathway lead to the metastable state S3, one can take a look at several important binding states along the pathway. And SILCS allow one to look at the per atom contributions to the binding in terms of grid free energy values. Shown on the left in the active site, the binding pulse actually reproduce the crystal binding orientation, and the protonated amidine group in benzimidine forms strong salt bridge interaction with D189. And this interaction is captured by the negatively charged frag maps, as shown in these cyan colored meshes. And the GFE values also tells the same story, where the amidine group being assigned a very favorable GFE value. Another binding pulse along the pathway captures the state when the molecule is coming out of the active site, with amidine group tilted outwards. And as indicated by the frag maps, this amidine group is still being accommodated favorably and can form hydrogen bonding interaction with the nearby glycine 212 main chain carbonyl group, but in a very less favorable way than that in the active site. That's why the overall LGFE is become unfavorable. And further on, when we come to the state that has the highest energy along the pathway, this state is partially stabilized by the hydrophobic contact with the nearby residue W213, and as indicated by the apolar frag maps as shown in the green meshes, the phenol ring gets slightly favorable values than the previous state, while the amidine group gets less favorable values. And when we come to the metastable state S3, the phenol ring in this pose is now in a more optimal position to form hydrophobic contact, as well as the amidine group forming hydrogen bonding reaction with the nearby Q175 residue. And the GFE contributions from amidine group is favorable, as shown here, like a negative 1.4 kcal per mole, while the phenol ring now has a negative 1.6 kcal per mole overall GFE value. This is more favorable than the previous state. So all the information together can give us a whole picture about the ligand unbinding process, and may be helpful to give insights on how we can optimize the ligand's kinetic profile. The states on the pathway also reproduce binding states captured by previously enhanced MD studies on this system. So for example, the circled state reproduced the TS3 state found by the MSM model, and the P state found by Tirari et al. Using the metadynamics. Since the SILCS kinetics was verified to be capable of reproducing energy barriers for the trypsin test system, we will extensively give it a test using more protein systems and more ligand and binding data. So 8 proteins were firstly being tested, and 2 additional proteins were added later as independent test sites. One can treat the ligand and binding process in a 2-step fashion. First, it can be relocated from the bound state to a metastable state on the surface where it is more solvent exposed, and then it can leave the protein to the bulk solvent by paying a free energy penalty, which is the large part comes from the hydration term. SILCS kinetics captured the pathways from the bound state to the metastable states on the surface. There might be multiple metastable states along the pathway where each barrier can be estimated. After reaching the metastable states on the surface, the LGFE value for this surface metastable states, here we noted as LGFEM, can be treated as the free energy penalty paid to go into the bulk phase. Since our GFE values are normalized to the bulk phase, thus LGFE in bulk phase will be 0. So the free energy penalty paid for hydration is already embedded in the LGFEM value. We're going to examine the energy barrier for relocating bound state to metastable state on the surface with and without the LGFEM term. And the GFE includes both enthalpy and entropy contributions to the bending of fragments. However, for ligand ensembled from fragments, the restraint energy part is ignored. That's why we also tested to include the intermolecular energy, IE, of a molecule in our energy barrier estimation. So in total, the energy barrier being estimated has 4 combinations, with and without the intermolecular energy correction, and with and without the LGFEM term. We calculated the Pearson correlation coefficient for correlation analysis between energy barriers estimated through our SILCS kinetics with the experimental negative log K-off values for all 8 tested proteins. The energy barriers estimated using the LGFE with the inclusion of intermolecular energy with the LGFEM term consistently give the good correlation with the experiment data, even though other ways can give better correlation in some cases. So this is about the last row, like for each protein. And we also tested a way to use the pathway predictions. So we tested only considering the largest pathway cluster, considering the low energy barrier, as well as to consider the average energy barrier for each ligand across all pathways. So using the lowest energy barrier per ligand gave the best consistent result across all protein systems, which is reported in the middle column for each protein. And shown here are the correlation plots for all the 8 tested systems. The lowest energy barrier per ligand across all protein systems have satisfactory correlation with experimental negative log K-off data. Beyond the energy barriers, diffusion also contributes to the bending process, which is missing from the LGFE profile. To consider more contributing factors, we intend to build a machine learning model using both energy profiles we got from our SILCS kinetics, as well as some static ligand features that can be linked to the diffusion process. For the 8 proteins, 235 data points can be stratified into training and test sites. We tried 2 types of machine learning models in order to use SILCS energy terms. One is the decision tree-based regression model, such as the random forest, in order to use the energy barriers as input features. And second is we can construct a recurrent neural network plus a multiple layer perception in order to incorporate the full energy profile into the machine learning model. So all models are tested using the test sets, as well as the 2 independent sets from the additional 2 protein systems. Molecular weight and number of rotatable bonds are used as input features in addition to the energy barriers, as well as the LGFEM indicator. And as shown here are the distributions of the negative log K-off values. And you can see both for the training set and the test set, we have representations for different negative log k-off values. So for the tree-based models, hyperparameters were trained using grid search in the defined hyperparameter space during the training through five-fold cross-validation. The hyperparameters from model with the best performance in five-fold cross-validation are selected for each machine learning method. The final model is trained using the full training set. So across all models, including RF, the GB, LGBM, and XGB, the random forest gave the best performance. And the feature importance are plotted for the final random forest model. It can be seen that the molecular weight has the largest importance, which indicates the importance of including diffusion term in our model. Energy barrier features, as well as the number of rotatable bonds and LGFEM, has similar importance, indicate their contributions to the model as well. And we also plotted the correlation between the molecular weight with the experimental negative log k-off values. And you can see the correlation in our data set is pretty weak. So that means the importance of the molecular weight alone cannot make the model more predictive. So that means all terms are needed in our machine learning model. Since different pathways has different lengths, and for the same protein, different ligand can choose different pathways, the energy profile per ligand is not well aligned and cannot be used as static features. In order to use the energy profile, we employed the recurrent neural network model, which can take a time series data as input. Here we adopt the bidirectional long-short-term memory RNN architecture. The energy profile per ligand is gradually fed to the network during training to learn the information in the energy points in both forward and backward directions. We have two layers of LSTM, and we also have a dropout layer to prevent overfitting. At the same time, the three static features are fed into a dense layer of neurons with a ReLU activation function. So the final outputs from the LSTM layers are concatenated with outputs from the dense layer to combine information learned from both energy profiles and static features, and then fed to another dense layer to further learn the data. The final output layer contains only one neuron in order to predict the experimental negative log k-off value. And as shown here, the hyperparameters are tuned using the Bayesian optimizer in the defined hyperparameter space. We stratified the training set of 190 compounds into 171 training and 19 validation subsets. And during the tuning, the model performance is evaluated on the validation set with the best performed model served. And you can see here, like it gets a satisfactory performance. So beyond the test set, we further validate our machine learning model using two independent protein systems, CKA and RIP1. So as shown in this table, you can see since the RNN plus MLP gives more consistent performance over different test sets, so these values are kind of similar to their performance on the other test set. And the random forest is a bit overfitted. But overall, the machine learning model can give very reasonable predictions. This protein test set is never been present in the training. So this performance is very satisfactory. Just a quick summary about what we got. So we have a pathway finding algorithm built using the SILCS energy grids, and the SILCS kinetics was verified to be able to capture meaningful metastable states on the protein surface. And this results in an efficient binding kinetics computational assay. And there are multiple informations could be utilized from this workflow. And we also constructed machine learning models in order to predict the experimental k-off values. And at the end, I want to thank members in our CAD Center and fundings from NIH, NSF, and the Waxman Foundation awarded to the CAD Center leader, Dr. Mackerel, are also acknowledged. If you have any questions about my talk, feel free to contact with me through the email listed here. And thank you for your attention.